Okay, thank you, Devajyoti, and let me thank the organizer again for organizing this very rigorous, long school and conference, which I think to interest to both condensed matter physicists, people working in quantum information and quantum gravity. Unfortunately, I couldn't attend many talks, but some of the talks I attended from other areas. I think I also learned some things, even though it's not in my area of research. Okay, so I'll be talking about something related to quantum measurement. So mainly this kind of topics which has become interesting in the question of quantum dynamics, which is how you manipulate systems by doing quantum measurements, manipulate thermodynamically large system by doing quantum measurements. So, so let me just to sort of, I mean, very basic things which all of us know. Just to sort of say this, so generally we are thinking about manipulating entanglement by doing measurements. Very characteristic thing is this Bell pair state, which has this maximal entanglement log 2. Now, if you have a superposition and if you measure, let's say this qubit, then you get with probability 0 or 1, with probability half 0 or 1. Similarly, if you let's say here in this Bell pair, if you measure one of the qubit, then you also get two outcomes and the state becomes 0 1 or 1 0. So you essentially by measuring you unentangle the state. Okay. So, so by measurement is destroying, at least this kind of measurement is destroying the entanglement. So now sort of iterating this, or you can ask whether actually you can manipulate many body states of extensively large system by just measurement. So for example, let's say you start with a state which is I'm showing it as a caricature where you have lot of entanglement shown by these Bell pairs between a subsystem A and other part. So typically this system has a, as the caricature suggests, a volume law entanglement. So effectively the entanglement goes as the size of this subsystem A. So now let's say you do these measurements like this, and the measurements at least locally it will project into this local basis. So you do these local measurements on the qubits, and then maybe it can destroy this entangled state and generate something which has much less entanglement. Okay, so which is like a area law. So effectively only having some Bell pairs between the A subsystem boundary with the B subsystem. You can ask even a question that just by measurement can you transfer a metal to an insulator, or even more strangely, let's say you can you by doing measurement can you convert an insulator into a superconductor or a superconductor into an insulator. Okay, so is this really possible? So, so this, so I'll discuss something related to that. So let me before that sort of just review very briefly some of the things that people have been working on this type of topics. So the main work that has been done in this area, asking these questions that how measurement can manipulate quantum many body systems and states, is comes in under this general paradigm of random quantum circuits with measurements. Okay. So again, so what is shown here in this picture is that you start with some states which are shown by these legs, which are some qubit state, let's say 0 1 1 1 0, some product state, and then what you do, you apply this in this particular case, you apply some 2 qubit gate. So you apply 2 qubit gate between 1 and 2, 3 and 4, 5 and 6, like that. So these gates actually entangle these 2 qubits which were initially unentangled. So it entangles this, and then what you do, you again apply at a later time, you again apply 2 qubit gate but different pair of sides. Okay, so like that you evolve. So if you just apply these gates, so then typically at a long time you will generate a lot of entanglement. So everything get entangled, and you will typically at long time steady state. So if you go on adding applying this gate for long time, you will typically expect to get volume law. Okay, entangled state starting from unentangled state. But now let's say this unitary gate you also interact by doing some measurements which are shown by these circles. So after each of these 2 qubit gate, you apply some local measurements, you measure these qubits with some strength. So let's say I have n qubits and I only measure p fraction of them. Okay. So if I go to p0, then I am not doing any measurement. If I have p1, I am measuring at every step all the spins. Okay, so then what will happen by tuning this P, you can actually tune this competition between the unitary entangling evolution and the non-unitary measurements. And the question is, can you get something interesting? And it turns out indeed you do get this. So what people have found out, a lot of numerical work, analytical work, so people have found out that you get these generic situations that when you have very small p, of course you get a volume law phase at long time. So at long time steady state is a volume law phase where the entanglement entropy of a such system goes like L to the power d. Now if you go on increasing p, at very large p you get this area law, everything get disentangled. But interestingly, in between you get a very interesting phase transitions, and this phase transition is a critical point which has some logarithmic scaling of entanglement. Okay, and it has a lot of critical properties, critical scaling and all, and people have tried to connect these transitions to various StatMech models and hence to CFTs. Yes.
What is the role of the randoms, the random unitaries?
Yeah, this is just to make the model simple. Okay, so these random unitary models, because you are applying random unitaries at each instant of time, there are some simple techniques by which you can solve these in certain cases.
I see. And is it also that do you have in mind like chaotic systems, or are you using this as a toy model for any system?
No, this is not a model for as such any system. It's just a, I mean, you can think of this as some quantum computer, of course, right, where you are applying this. So ideally, of course, these unitaries are drawn from some Haar measure, but you can change the measure also. But you are thinking really about this kind of quantum computers. Yeah. Okay, so what you find here, so what is shown here is this entanglement entropy as a function of the subsystem size, or in this case just the system size. So I am just measuring the bipartite entanglement entropy as a function of system size. So as you can see that when I have p equal to 0, if you can see this, so then you have a volume law. So the entanglement entropy of subsystem goes linearly in L. This is a one-dimensional system, so volume law is just linear in L. So you can see that this volume law. Now as you increase this strength of measurement, so this slowly goes down, it reaches a critical phase, and after that it basically gets saturated at large L. So meaning that you are getting an area law in 1D which is constant, doesn't change as a function of L. Right, and this is where you see this critical point. Yes.
At this critical point, you're saying some logarithm scaling with it. Yes. So only the entanglement entropy is your order pair. You're not considering anything else.
No, so in these particular works, they mainly look into entanglement entropy, but people have looked into other type of diagnostic also, like as a order parameter of these transitions. So there are different kinds of other order parameters that people have come out. All of them are sort of related with entanglement. Okay, I mean you can sometimes put an ancilla qubit and couple it with the system, sort of create an entangled state and see how the entangled state goes away. Okay, so this is just a motivation. I am not directly going to talk about this, but this is an example where you can, by doing measurement, you can manipulate the state of this many body system by just doing measurements and this. Okay, so what I am going to discuss is sort of a related topic, which in the first slide I sort of tried to motivate, which is can you actually induce phase transitions, okay, between states like superconductors and metals or superconductors and insulators by doing measurements, extensive number of repeated measurements. So this is a work done with a very bright undergraduate student at ISC, Purnendu. So this is not published, but yeah, something that we are writing up. So okay, so the setup that I am going to consider is a model. It's a very well-known model in condensed matter. It's a model of what are known as these Josephson Junction arrays. Okay, so these Josephson Junction arrays are essentially a lattice model where each lattice site corresponding to some kind of a superconducting island. Okay, so imagine that you have some kind of thing that you have prepared where you took sort of a mesoscopic size superconducting island and then put them into a lattice. You can do it in experiment. I will show a picture next slide. And then what happens that these islands are weakly coupled by Josephson tunneling. Okay, so essentially they are coupled weakly. So you have the Josephson coupling. So each island has a well-defined gap, a superconducting gap, but it has a phase. Now these phases of two different islands nearby, they get coupled by the Josephson coupling. And moreover, because these are mesoscopic islands, so these also have a number fluctuation of Cooper pair. Okay, so the number of Cooper pair can fluctuate, and this Cooper pair number is just related canonically with the phase. Okay, so this is the model. So this model basically has two terms. So one term which is like a Josephson coupling term, which tries to make all the angles of this all the superconducting island to be in phase. Okay, whereas this other term, which is like a kinetic energy term, which is like this Ni, which is the number of Cooper pair on the island, that gives the fluctuation of this phase, and that tries to destroy this phase coherence. Okay, and then make a transition into a state which is just superconducting island without a phase coherence. So that in this context will be called a insulator. Okay, because so you in this model you go from a superconductor to an insulator, because without this Josephson coherence you will not have any kind of non-zero resistance in this state, so you will have some finite resistance. Okay, so that's why it's called insulator. And this strength of this is controlled by the capacitance of this this island. Yes.
Also don't have phase coherence, right?
Yes.
So why is this the diagnostic for an insulator? It could
no, but this model, what happens is that because these are only Josephson coupled, so there is no other way to conduct electricity.
Oh, okay.
So when once you lose superconductivity, you don't you behave like an insulator.
I think so.
Yeah. Okay, so this is a old picture of this from 1990s. So this is basically showing this Josephson junctions with some weak links connecting them. So these are, I think, these islands, and then they're connected by some weak links, some tunnel barriers. So you can really make different kind of lattices of these objects. Okay, and this is what I was showing. So so here again you try to change tune this parameter that I mentioned, effectively this Josephson coupling and the capacitance. And what you see here is that when you have large coupling compared to this capacitive energy, so then you get a superconducting transition as a function of temperature. It goes to a superconductor, you have a zero resistance. Okay, whereas if you tune this thing to a smaller Josephson coupling, then you see this insulating like resistivity, right? So that's what I was mentioning. And then there is some intervening critical point. So you can do it at very low temperature. So this is really a quantum critical point. Okay. And you can also see this experiments and theory of certain approximate theory. You can actually see this is shown as a function of the ratio of the charging energy to the Josephson coupling as a function of temperature. So when you have a low charging energy compared to the Josephson coupling, you get a superconducting state, and as you increase the temperature, it goes to a resistive state, normal state. Okay. And then as a quantum phase transition at low temperature, you can go from a superconductor to insulator by just changing the charging energy with respect to the Josephson coupling. Okay, so this is a well known to be a good model. This model well known for this, and this is so some of course this model is not exactly solvable, unlike the transverse field Ising model in higher dimension. So generally you do some kind of variational theory for this. Like standard mean field theory, so which is essentially just decoupling, just like Ising magnet mean field theory, you just decouple this interacting term in some single side term, and then define an order parameter, which is this expectation value of cos theta, and here it is shown a phase diagram as a function of this ratio of Josephson coupling to charging energy, where you go from insulator to a superconductor, and you can see also the order parameter, which is just the expectation as a function of this coupling at zero temperature. So again at zero temperature you have an insulator to superconductor quantum phase transition through a second order transition, okay, where the order parameter continuously changes. So now there are different approximations. So it turns out that it is this mean field theory doesn't capture some important fluctuation effects. For example, if you are at low temperature, you have a U1 order parameter here. So there is a Goldstone mode, and so these Goldstone modes are basically the phase mode here, and these phase modes are not captured. So to capture them, you can try to do some modified variational theory, which is called the self-consistent harmonic approximation. So effectively, you treat this interaction term by making it a quadratic term, where you keep the coefficient of the quadratic term as a variational parameter. Okay, and so this is essentially like a superfluid stiffness of this model. And when the superfluid stiffness goes to zero, it's an insulator. When the superfluid stiffness is non-zero, then it's a superconductor. So that's how this theory describes this transition. Okay, and again you can see this transition there are some difference between these two theories, two approximate theories. Typically, this theory will give you a first order transition, whereas this gives a second order transition. Okay. Anyway, so this is the sort of the basic theory that you can do in this case. So now one sort of interesting experiment work that was done here. So which is which will be sort of connected to what I am going to talk about, which is this measurement induced transition. We will see that there are some similarities between this case. So there were some experiments in 1980s. What they found. So this is the same kind of systems, but not exactly this artificially created Josephson junction. But what you had a granular superconductors. So sort of disordered superconductors, but these Josephson junctions are some good model for this kind of granular superconductors. Okay, and what they found that in this kind of granular superconductor, it seems that this transition from superconductor to insulator actually didn't depend on the ratio of EC by EJ. Okay, so even though from whatever I discussed, it seems like that it should depend on this charging to Josephson ratio, but in this experiment it didn't depend. Instead, it depended on the normal state heat resistance of this system, which is basically if you go to the normal state, there is some resistance, and that resistance essentially controls the dissipation in the system. Okay, so it was kind of very a strange phenomena that you had some kind of a thermodynamic phase diagram which actually dependent on resistance, dissipation. Okay, so this of course I don't think this is completely settled, but people came up with model for this, which are interesting model on their own right. So the model they came up with is essentially a dissipative Josephson junction. So what you imagine here, that you have the same Josephson junctions, these arrays, and then in addition you have some environment or some bath, which are some bath of oscillators, which are coupled to this this Josephson junction, these phases, basically this phase difference. So remember, the phase difference is a gauge invariant quantity, and you can couple this gauge invariant quantity to some bath variables, and then so this bath basically gives you the dissipation. Okay, and you can write integrate out the bath. It's like a caldera Leggett type model. You can integrate out the bath, and you can write effective description in terms of some action where this dissipation enters through this term, which has this characteristic mod omega n, which is a coefficient of this term which actually determined by the normal state sheet resistance. Okay, so this dissipation strength alpha actually is inversely proportional to resistance, or is proportional to the conductance, and it controls the dissipation in this system.
It's not a time reversal.
No, it's not. Right, so this was the model, and they did some simple theory for this, and this is the phase diagram they found. So what they found is that if you look into this phase diagram, now you have another axis which is this dissipation. So you are looking at zero temperature. So when you have zero dissipation, this is what I earlier discussed. So you have a quantum phase transition. So as you increase this coupling J by EC, you should get a insulator to a superconductor. Okay, so I am just calling it normal state, but it's really insulator to superconductor. Now you increase the dissipation, so then of course this, as you increase the dissipation, you expect of course the effectively, so what you find that somehow the superconducting state get enhanced, like the insulator is actually shrinking, and in fact what they found that if you increase dissipation, value of dissipation upon certain number, which is actually turns out to be just dependent on dimension 1 over d. Okay, d being the dimension. So then you get this completely vertical phase boundary where the transition doesn't really depend on J or EC. Okay, so it just depends on dissipation. Okay, and then you go from an insulator to a superconductor, and this state at zero temperature is a superconductor. So effectively, what is dissipation? So the way you understand this is what dissipation. So the reason the superconductivity was getting destroyed is because of quantum fluctuation. Okay, because of the charging term. So by putting dissipation, you are actually killing these quantum fluctuations, and that actually helps superconductivity. Okay, so it actually stabilizes superconducting state by dissipation. So this is the mechanism which is understood in this material, and what you find here is that this transition, when you have the transition which depends on J by EC, is first order, whereas here this vertical line where you have transition completely controlled by the dissipation strength, which is exactly given by 1 over d in some dimensionless unit, this is actually a quantum phase transition, is second order. Okay. And it is independent of this Josephson junction coupling. Okay, so now, so this the reason I told you, so now what I have discussed is of course a system which is like a standard system, so a standard system, a closed system or a system with a bath, in that case you have a dissipation. So now we are going to consider a completely different system, so I will be thinking about an isolated system, which does, isolated meaning that it does not have a bath, but I will of course still do some measurements on this system. So there is no heat bath to this system, okay. So the system is a closed system on its own, and then I am going to do some measurements, and I am going to ask that what happens to the non-equilibrium steady state of this system. So I will be doing this measurement again and again repeatedly, and we will reach a steady state, and I am going to ask whether this steady state can be superconducting or it can be insulating or something else, okay. So that is what I am going to do. So for that I am going to consider a model which is a generalization of a well-known model for weak measurements. So this is a well-known model which was developed by these people, Caves and Milburn, to describe a weak position measurement of a single particle. So this kind of model is quite used in this literature, and I am going to use this model to write a model, a measurement model for Josephson junction arrays, okay. And what I am going to ask is that this model will also seem like that there is some kind of dissipation, because you are measuring something and then some energy you are putting, so there is some kind of dissipation in this model. And so the question that I am going to ask is that this dissipation because of measurements, which I am calling monitoring, is it similar to the dissipative model of a bath, or there is a difference between these? So that is the question I am going to ask. So let me take you through this model slowly. So the model has these two parts. So I have this earlier Josephson junction Hamiltonian that I showed. If you remember, this has some sides which I am just drawing in one dimension here, but it is not important that it is in one dimension. So I have just these sides in one dimension. I have this superconducting islands. And then this is described by this Josephson junction array model without any dissipation or anything, just only the Hamiltonian term without the bath. And then what I am going to do, I am going to couple this system. In fact, so I have basically for each pair of sides I have a phase difference. So this phase difference periodically I am going to couple to a detector, and this detector is a quantum particle which has a position and a momentum, okay. And this detector, what it does, that it in discrete time, each interval of time tau, basically all the phase difference couples to different detectors. So these detectors now have, the detector is a quantum particle, it has two levels. It has the levels, two levels. The one level is just the phase difference, this pair of sides I and j, and then I am switching on this detector by this delta function coupling at some instant of time n tau. So they have also an index n, okay. So every time I am coupling them, I am thinking of bringing a fresh set of detectors, and this detectors is getting coupled. I have still not done any measurement, okay. It's just a coupling, some kind of a kick that I am giving, delta function kick, okay. So basically by this what happening is that the system between, so I am doing measurement in interval of time tau. So between two intervals Tn minus 1 and Tn, the system just evolves with a unitary evolution of this Josephson junction, okay. And then at this time instances I am getting coupled. So before I get, sorry, this is not very visible, sorry for this, but so what is happening is that some time Tn minus before this time Tn, just before this time, what I do is I prepare my system, I have a system and I prepare these detectors, which is a quantum particle. Each detector I prepare in a Gaussian state, okay. So each detector is prepared in a Gaussian state which is characterized by a standard deviation sigma, okay. So this is the wave function of the detector at Tn minus. Now at Tn, at this time, this get coupled to the system and so get entangled with the system. Because of this coupling, this detector get entangled because you have an interaction. And then at Tn plus, what you do, you measure the position of the detector projectively. Okay, so detector is a quantum particle which has position, so I just measure the detector position. So it will give me a set of readings. And these readings will depend on what the history of the measurements, right? So I do the measurements, the detector gets collapsed, the system gets changed because it is entangled. And then again I do another set of measurements, so I keep all these readings. Okay, so these readings give me a trajectory which is called a quantum trajectory. Okay, so I can have, so when I do this experiment different times, I will get a different trajectories. So I will get many trajectories if I repeat this experiment many times. Okay, so that's what is called a quantum trajectory. So now it turns out that for this system, you can write down a description, a time evolution of the density matrix, so which I described in the earlier slide. So you have, let's say, some density matrix at time n-1, and then what we are doing, so before I do the next measurement, the system evolves with this unitary evolution, which is because of the this unitary part, the Josephson junction. And then after that I am doing a measurement. So this measurement is this measurement is encoded by a non-unitary operator. Okay, because I am doing these are called the Krauss operators for this measurement. So you basically have a non-unitary operator which you can show, and I am only looking into the evolution of the system density matrix. Okay, so this is only the system density matrix. The state of the detector has been projected. Yes.
You talked about, you're going to do an ensemble average or something.
Yeah,
it's called a weak measure.
Yeah, I'll show what kind of average. Yes.
And then the detector periodically couples to the system.
Yes. Just before the measurement, detector gets coupled. Then you do a measurement and you get the reading and you throw those detectors. When you do the next measurement, you either bring phase detector or you initialize the detector to a phase. So there is no memory for the detectors. Okay, so it turns out that if you just go on doing this measurement, then this system will actually heat up. Okay, so something like what Diptarko was telling, because you are just doing periodically doing this kind of effect, so it will just heat up. To get rid of this heating, so what you do, which is known in this kind of literature of quantum trajectories and quantum information, you do what is called a feed forward or feedback. Okay, so you basically take the reading and you try to correct. So what this does, so when you do the measurement, essentially the system gets a kick, and it's the number, or in this case the number of the Cooper pair changes, and it sort of can get heat up. So you try to correct this, you try to correct the change in the number by putting a feed forward. By taking the outcome of the earlier measurement, you try to do a unitary operator so that it on average try to bring back to the earlier state. Okay, so this is a unitary part and this is the non-unitary part. So this together make this Krauss operator, and this feedback part essentially acts like a dissipation. Okay, because you are just giving a unitary energy cost there in some sense, and it acts like a dissipation. So now it turns out, so of course this model you can consider in a discrete time limit. Now we are going to take a continuous time limit, that's why it's called continuous weak measurement. So what we are going to do is take a limit where this measurement interval I am going to take to 0, but at the same time I take this sigma, which is the wave function of the detector, which essentially measure how strongly you are doing the measurement, I am going to take to infinity. Okay, so and I am going to keep this sigma tau finite. Okay, so this is the limit where it is become a continuous weak measurement. So it's basically like you are doing the measurement too often but too weakly, so that there is a fixed limit of this. Okay, so if you are making tau going to 0, you are measuring too often, but if you are making sigma infinity, you are making the measurement too weak. Okay. So that basically defines a measurement strength, or inverse of this essentially defines a measurement strength. And it turns out in this limit you can write a field theory for this non-unitary evolution using again a Schwinger-Keldysh path integral, but it's a non-unitary field theory. So it has the non-unitary evolution, but you can obtain it. And this field theory actually depends on the reading, okay, on the trajectory. So the field theory I have written right now has not been averaged or anything. This field theory is just for a given trajectory. So now, so this is the, for this Josephson junction, this is the thing that you get. Again, the details not so important, but you get a field theory on this Keldysh contour. So now I come to this, what kind of averaging that you do. So it turns out this entanglement transition that I discussed earlier. So that entanglement transition you can only see if you average the entanglement entropy, okay, which is different from averaging the density matrix. So typically when you discuss this system, there are two approaches. One is this Lindblad approach, where you basically look into the average density matrix average over all measurements, and that actually cannot show you any entanglement transition. So you have to measure quantities which are non-linear in density matrix, like entanglement entropy. And then if you do averaging, then you will see this effect of entanglement transition that I showed you. So that's why it is very difficult to do in experiments, because it has this problem of post selection, which people are still trying to deal with in experimentally. Here, in this particular case, I am going to take a much simpler approach. So we of course are looking into also individual trajectories and all, but for this rest of the talk, I am going to discuss where I am going to look into a average over the measurement outcome. Okay, so it should have a Lindblad description. So this is the phase diagram that one gets, okay, of this problem. So if you remember, I showed you earlier some phase diagram for a dissipative model. Again, sorry for this thing. So what it is shown here is the Josephson coupling J by EC as a function of the measurement strength. So remember, delta inverse was measurement strength, which is sigma into tau. Okay. So what I am showing is this. So what you see here is again, so in this system there is no, as I said, there is no bath or no temperature from outside. Okay. So I am just doing this measurement. I am getting a non-equilibrium steady state, and I am just doing a theory for the non-equilibrium steady state, assuming a steady state. And then you find that there is a transition. So there is actually first order transition from an insulator to superconductor as a function of this. So I will contrast this with the dissipative case, but the main thing is you see there is some re-entrant transition. Okay, so you can see that something as a function of measurement strength initially could be insulator, then it becomes superconductor, and then again it can become insulator. So that's the phase diagram that you get. So this is like a measurement induced phase transition. Okay, so I don't have any external bath, no temperature, nothing, and I am tuning the phase diagram just by measurement. So indeed you are making an insulator to a superconductor and superconductor to insulator by manipulating measurements. And now to compare with the dissipative case, you can try to look at this Keldysh field theory in more detail. So the main thing you look at is this kind of Green's functions of the theory. Because effectively we are doing a effective quadratic theory, self-consistent quadratic theory, which is the self-consistent harmonic approximation. So you can look at the Green's function, right, which are given by that, and then using this Green's function you can calculate self-consistently the superfluid stiffness, and it has some dependence which you can find out. But the main interesting thing here, you can try to compare with the dissipative case which I showed earlier. So, so this feedback that I gave, so that is basically like a dissipation in the dissipative case, which was this alpha, and then you can also try to define this type of theory by a fluctuation dissipation ratio. Okay, so in Keldysh theory, if you take the ratio of the Keldysh Green's functions to a combination of the other two Green's functions, which are not independent, then you can define a fluctuation dissipation ratio. For example, in the thermal case, like the dissipative case, it will be just given by cot hyperbolic h bar omega by 2t, and the temperature here determines this. In this case, there is no temperature because there is no bath, but it turns out that at low frequencies, at small h bar, still you look like that you are having a classical limit of this fluctuation dissipation ratio, which is like if you expand this for large temperature, then you get 2t by h bar omega. So here also at the lowest omega, you get a effective fluctuation dissipation temperature, which is called the T effective. Okay, so this T effective is completely controlled by quantum fluctuations and the measurement strength. It doesn't depend on any external thing. So it's like you can say a quantum heating. So this system, basically get a temperature just from quantum measurements. Okay, so there is no external temperature. So this is the effective description. However, if you go away, if you go to lower temperature, lower T effective, then of course this approximation is not valid, and then you get a correction, and this correction is very different from the thermal fluctuation dissipation, because this series doesn't truncate for the thermal fluctuation dissipation, where this is exactly given by these two terms. So at lower temperature they are very different, and there will be difference between these two systems. And indeed that's what you see. So I showed you these two phase diagrams, the contrasting phase diagrams. So in this case I can compare the dissipation, and in this case the feedback, and as you can see the phase diagram is very different. In this case I actually, large dissipation I got a superconducting state. Here large dissipation actually destroy the superconducting state. You can also compare the phase diagram in terms of this effective temperature. So if you look at the dissipative case, then at low temperature you can get a superconductor at large enough values of the Josephson coupling, and as you heat up, then the superconductor will be destroyed by some thermal transition. Whereas here what you find that here for this coupling this is what happens, but if you go to larger coupling, you can in fact get a insulator. Initially at low temperature you can get a insulator, and by temperature it can become a superconductor. So by heating a insulator you can make it a superconductor. Okay, so this is of course not a true temperature, it's the effective temperature, but this kind of manipulation that you can do with a measurement. So something which is low temperature insulator and high temperature superconductor. Okay, so all this kind of weird thing you can get here. So I'll just end in 2 slides. So this calculation that I showed is a very simple variational theory. You can ask whether these calculations or these results are robust if you include fluctuations effect. And we can analyze this in certain limit by going beyond this theory. I will not go into the detail of it. So for example, you can look at this theory in a limit, a semi-classical limit where h bar is small, and in that case what you can show that the dynamics of the equation reduces exactly to a stochastic Langevin equation, where the noise is controlled by a temperature which is the same temperature that I showed. So if you make h bar very small, so then this equation looks like a stochastic thermal Langevin equation, although the noise is not coming from any thermal bath, it is just coming from quantum measurements. Okay, and then in that case in 2 dimension we would expect this transition to be BKT and other things. Okay, so within these descriptions, you can also look at a very large damping limit, the large dissipation limit. You can sort of do a device into fast and slow modes, and you can again try to look at the slow modes. And the main thing to know here that even from this analysis what you see that if you increase the dissipation, then in the measurement case if you have large dissipation, then effective Josephson couplings goes to 0 or goes to negative. Essentially it means that large dissipation it will get destroyed, unlike the case of the dissipative one where large dissipation you can show that you have a large effective Josephson coupling. Okay, so you can see this analysis beyond this mean field analysis also these results are valid, that is large dissipation, this will give you an insulator and this will give you a superconductor. And you can do also some kind of weak coupling RG, and that also kind of agrees with these results and shows very different results. The RG equation shows very different results between this dissipative case and the measurement case. Okay, so the RG flows changes. Okay, so with that I will end here. So just to say that with measurements it seems that you can manipulate many body states in interesting ways, and that can give rise to phenomena which you don't really expect in thermal systems. It can in fact by temperature it can make an insulator a superconductor, okay, and by measurement. Okay, thank you.
Do you have some intuition for why the measurements have such a different effect from dissipation?
Not really. I mean, somehow, yeah. So we don't have any very good intuition. So certainly, okay. So again, I mean, this is sort of a mathematical intuition, as you can see. This is what I was trying to show. So the noise due to measurement, which is essentially encapsulated by this effective temperature, you can see that is very different. Okay, so even though it looks like that both are giving some kind of quantum noise, quantum thermal looking noise, but this noise for the measurement case is kind of quite different from the thermal case. Okay, so Yes, that's right. Yeah. So this kind of similar phenomena is known in some contexts which are called quantum heating. So where also by sort of Floquet drive and some dissipation you can actually tune systems where some system actually has a temperature which is generated from quantum effects. Okay, so something similar to this happens here, but I don't have a very good physical understanding why these two are very different. But at least mathematically the noise spectrum looks very different. I mean, this is much simpler, but it has some effects. It has important effect as a result.
Thanks a lot, Sumilan, for a very interesting talk. There's something I didn't intuitively understand. So you had a detector which was coupling, of course, to these Josephson junctions. Was it measuring the phase of the junction?
Yeah, phase difference.
The phase
yeah, I went
difference
probably
between-
too quickly. Phase difference. So because the phase difference is the gauge invariant quantity.
Yeah.
So you couple it to the phase difference. So it is measuring the phase difference. So in some sense, it is also doing a similar thing like dissipation. So if you are measuring the phase difference, you are fixing the phase difference, right, by this measurement.
Yeah.
So that will destroy the quantum fluctuation, because the quantum fluctuation is the fluctuation of Cooper pair number. If you fix the phase, that fluctuations will be reduced by this measurement, right. So basically you are collapsing into a fixed phase difference. So that's why you think that it will affect the it will help the superconductivity, just like in the dissipative case, but it seems it is not doing if you are taking this, and that is probably becoming because of the feedback. Because it's not only this measurement, I also put a feedback, right, and the feedback is working like a dissipation. And this dissipation is, I think, very different, even though intuitively I would have thought that this measurement would have done the same thing, fixing the phase and then enhancing the superconductivity, but it is not doing that.
And just once, what was the feedback like?
Yeah, so feedback, yeah, the feedback I'll show you. Yeah, so the feedback was, so you first measure this phase difference, okay. So you measure the phase difference, and then what happens is if you measure the phase difference, it essentially you can show that the number of the Cooper pair gets a kick. Okay, so it changes like there is a sharp change of the number. So what you so you try to correct for that number on average. So you try to sort of give this measurement strength, and let's say your number difference has increased by some amount, you try to reduce it. If number difference has decreased by some amount, you try to enhance it. So that's what this term is doing, the feedback term.
This sort of measurement-induced phase transitions can help in designing, let's say, a room temperature superconductor.
Could be, yes. I hope so.
That'll be cool.
Yeah, not possible. No. No, you can realize this. I mean, in the at least in this kind of quantum computers, right? I mean, small system, yes, but in a larger system, this kind of IBM computers, probably you can do this. Yeah, right. So they actually do it. They manipulate a topological state by measurements, right? So you can do it, but question is how long you do it. I mean, generally you expect to do it over some finite depth of this circuit and reach a state. So those kind of thing I am not concerning me. I mean, I am just thinking infinite time, right? So and yeah.
Yeah, maybe I didn't fully understand, but like, if is there a sense in which you keep do the keep doing evolving with the measurement, but then if you switch off, you continue to get the super phase for a while and then it stops. Is there
Yeah, so if you don't continue to do the measurement, right? That's what you are asking. I stop there and then I just evolve.
You do it for a while and then like I'm wondering like how long would the
so I mean, okay, that's a more detailed question, but again, I mean, I am only looking at your non-equilibrium steady state, right? So of course, if you stop the measurement and then evolve again, it will get entangled, right, as you evolve. So because I am looking into the non-equilibrium steady state, which is t going to infinity, I am not looking into that question. So those are interesting questions, that how long it will again take to get entangled. Let's say I disentangle the system, right, by this measurement, and then I leave the measurements and again evolve. So how long does it take to disentangle?
I don't know if the parallel I find is like related, but like you would have heard about this traversable wormhole story. There also you do some measurement and then for a while you get some non-trivial effect. And then this. this is a window for which you get the non-trivial effect. But it's something very
but here you are
non-unitary
doing,
like this.
so people have also done things like one-shot extensive measurement. So let's say you take some interesting state, some CFT state, and then you just do a one-shot extensive measurement. So you can actually change the correlations. So these people have looked into in the context of Luttinger liquid. So you take a Luttinger liquid and you just do a one-shot extensive measurement, not many steps, just a single step, and then you can actually change the Luttinger parameter basically, the correlation function. So you can actually change the correlations of this many body state. So that's a single shot. What I'm doing many measurements. Of course, what you are saying in between, let's say I do some measurements and stop, and then I see in the interval what happens, right? So that kind of thing I have not looked into. Yeah. Thank you.